We are going to present here the Hellmann-Feynman theorem, which is really easy to prove and it's very useful as well. So let's consider we have a Hamiltonian which depends on a parameter, and we call that parameter lambda. On the other hand, these C lambda are the normalized variational solutions, including particular eigenstates of this Hamiltonian. And of course, as this Hamiltonian depends on lambda, the wave functions are going to depend on lambda as well. So once we have these wave functions, we can calculate the energies associated to that wave functions in the usual way, which basically is the average of the Hamiltonian calculated on that wave functions. And as all of this depends on lambda, of course, the energy is going to depend on lambda as well. So this is the Hellmann-Feynman theorem, which basically says that the lambda derivative of the energies of this lambda dependent on energy, can be calculated just as the average of the lambda derivative of the Hamiltonian on the same eigenstates. So as you can see here, there is no lambda derivative of the eigenstates, even though they also depend on lambda. So doing the lambda derivative of the energy, it's really straightforward. And the proof, it's really simple, as you can see next. So when doing the lambda derivative of the energy, which in principle you have to do, of course, the lambda derivative of the eigenstates and the lambda derivative of the Hamiltonian, we are going to split that lambda derivative in two different contributions. Here in the first one, we are going to do the lambda derivative of the on the eigenstates, and the second one we have the lambda derivative of the Hamiltonian. So in order to do the lambda derivative of the eigenstates, we are going to call this lambda dependence on the eigenstate lambda prime, and we are going to do the lambda derivative. Instead of doing on lambda, we are going to do on lambda prime, so that we are not doing the lambda derivative of this Hamiltonian term. And then after doing the lambda derivative, we are going to take lambda prime equal lambda. So as this C lambda is a variational solution considering that Hamiltonian, we have that the lambda prime derivative of this term, it should be 0 because of the variational principle. So there is no such contribution on the lambda derivative of the energy. The only remaining one is this one, and this is actually the Hellmann-Feynman theorem we have here. And as I've said at the beginning, that's easy and that's really useful because, for example, among other things, that's used in order to calculate the forces on the atoms. So basically, you just have to calculate the energies that the atoms or the structure have in order to calculate the forces on the atoms. Or it's also applied in the adiabatic connection formula. So it's really useful. And next, we are going to see the relation between that Hellmann-Feynman theorem and how it could be used in order to calculate the forces on the atoms.